Starting our lecture. First, I suggest to go through the reflections very fast. If you have any questions, please let us know. Otherwise, going to the reflections and go to the new lecture and a little talking about projects, if you'd want to do the project, and then the quiz. So let's go to the reflections. Reflection and Boolean algebra. There were two reflections, overflow and multiplexer. Yes? Are you with me? Perfect. Good. Overflow. Let's see, how did you write? Let's go to the last person who posted, not the first person. The last. Chloe. You are the last? Oh, you are usually the first. Okay. So overflow. Overflow. What was the question? I don't know what was the question. What is the question? Why is overflow detection important in signed addition? What are the potential consequences of not detecting overflows? Okay. So this was the reflection question. And Chloe says, overflow detection is important to determine if the output is in the current range to be represented by the given data type. Okay, perfect. This is important to ensure that your system function give accurate output. Yeah, in that case, yeah, it's good. Overflow, Jeff, oh, okay. Overflow can easily occur if two signed binomials are added and exceed the data limit. Not detecting can lead to two positive. Two positive? Oh, okay. Yes, two positive numbers being added together resulting in negative. Perfect. That's the complete answer. Kalan. Kalan is here? No? Okay, so that's good for overflow. Let's go to multiplexer. Select something from the middle. I don't know, going here by random. Ismail. Ismail is here? Okay, Ismail. What was the question? Multiplexer, yeah? How does the concept of a multiplexer enhance the efficiency and functionality of digital system? So I hope that you have given us a good example. Ismail, okay. It enhances the efficiency and functionality of digital systems by allowing multiple input signals to share one device with selection outputs. Very good. That's good. So we have several inputs, and based on the select, we will use one of them as the output. Rahima. No. Rida. Absent? Oh. Fadi. Okay, so we reach to Fadi again. It enables multiple input signals to be run through one device. It is accuracy that can be measured by the level of signal distortion that occurs as input is fed. I didn't understand this. What did you mean? It is accuracy that can be measured. You mean its accuracy, huh? Can be measured by the level of signal distortion that occurs as input is fed through the device. Could you explain? What did you mean?
Actually, this sentence has the same first sentence. It means we have many inputs and we have one output.
Okay, but its accuracy and signal distortion, these things, what are they? I don't understand. Do you have any idea? Any comment? I didn't get it. Okay, but the important is this one. There are, yeah, the multiple input signals, but I didn't get the next one. Okay, very good. So let's go to the lecture. Okay, what did you? I guess we were at this stage. Yeah. Am I right? We didn't go through that. No. Okay. So up to now, I tried to show you that a function which could be also represented by a truth table then we can play with the function and try to simplify it to make a better design, less gates, with less gates. So this is what we tried to do. And what we have done was some kind of ad hoc system, ad hoc method. We try to factor this, but we might add something to that, and then these go together, something that we have done during the previous examples. It was some kind of ad hoc intuition. You might get the best result or not. But here we are going to talk about a systematic approach that will ensure that we will find the best answer, the best simplified answer which would be possible. Okay? So this, we call it logic minimization. So what we have covered is we saw the realization and ad hoc simplification. Now we go to a method which is based on a Carnot map, and then we talk about a little about timing at the end of the lecture. Maybe Fadi was referring to the timing for distortion, so we will talk about it later. So we saw this example. I guess this is the overflow detector, that the sign of A and B plus the sign bit of S, the sum of these two, will generate overflow. If we have talked about it, if A and B is 0, but S is 1, there is overflow. And if A and B are 1, and then S is 0, then we have overflow. Otherwise, we don't have overflow. And that was the result. And also, we tried to make it a NAND-based circuit. We first tried to use it using AND and OR and NOT. And then we converted to NAND, and it happened. It was the result. The thing that you could see here is the result of an AND. A NAND gate, making it a NAND gate. Okay. And this was the function. Okay. Let's count the transistors that I tell you. This is the first design. In the first design, this is a 3-input AND. A 3-input AND has 8 transistors. 2 transistors for each input and 2 transistors for negating. It has 8 transistors, 8. This one is a 3-input AND, so it has 8 transistors. Or 2-input OR has 2 plus 2, 4 plus 2, 6 transistors. And also we have 2 for the inverters. Each inverter has 2 transistors. If we have time, I try to show you the transistor level of the gates. It will give you an overview of what's happening beneath the gates. But for the time being, just look at the numbers. So yes, this is 28 transistors. But with the NAND gate, this NAND gate, 3-input NAND gate, each input has 2 transistors. And so it has 6, it has 2 to the 4, and the rest are 2, 2, 2. And if you sum up, it will become 22 transistors. So you see, with some kind of simplification, some kind of change to NAND gate, we have 6 transistors less. And it is too much, 6 transistors in 28. Yes, please. What?
Is the goal always to minimize the number of transistors, or are there situations where you wouldn't mind having 3 more if it makes your design simpler?
Yeah, it depends. Yeah, I cannot say absolutely, but the main rule is to have less transistors. I should think of a case that maybe more transistor would make better layout. No, I don't think so. Less transistors would be better. If we are doing in a system like CMOS. This is CMOS. I am talking now about CMOS system right now. Complementary MOS. Each gate has one NMOS and one PMOS transistor. I will show you later, maybe if we have time. When I want to talk about the timing, I will show you transistor level, and then from there I give you some timing. So again, let's see this example. W is A and C, or by B and C, and or by A naught and B. This is the function. So how could we implement it? Yeah, you see A naught, B is one, and then A, C, this is C here. AC is this one, so here is AC, here is A naught B, and BC, C and B, and that here is BC. And they are all OR together, so this is the W. Again, I want to simplify it. How could I do that? As I told you, we tried to use intuition, ad hoc, so let's play with it and see what happens. What I do right now, I try to add and a 1 to this sentence. This term, BC, I will AND it with 1. Is it okay? Any sentence could be ANDed with 1. So this is 1, A plus A naught. So it becomes this, A dot AC plus ABC plus A naught BC plus A naught B. Now, if you look at these absorption, either you tell it is absorption or you just make it like this. So this is A naught B plus A naught BC. This is absorption. So the result would be A naught B. And here we have AC plus ACB. So this is another absorption. So the result would be AC. So it becomes AC plus A naught B. Okay? AC plus A naught B. From the this which had 3 terms, AC plus A naught B plus BC, we removed BC. Now this has 2 terms, which is simpler than that. But how did I do that? How did I find out that I have to add A plus A naught, AND it with that, and then get some result, and then do absorption, and then make it simple? It's maybe practice, maybe intuition, or maybe a systematic way that it will give me the result, and then I try to show it to you. I knew the result from the other ways, then I will try to reach it. So this is them. And now, with this circuit, with this design, AC plus A naught B, we can also change it to 3 NANDs. AC, this is an OR gate. Or if you make it 2 NOT. Not the same. Not is the same. So the first NOT, De Morgan, will make it NOT of this and NOT of this. So it will be NOT of AC and NOT of A naught B and ANDed together. And this is the other NOT which is there. So if you look at this is 3 NAND gates. This is NAND of AC, AC NOT. This is NAND of A naught B, so A naught B NOT. And this is, the whole thing would be the NAND of this and this. Oh, the circuit is much simpler, with also NAND also. If you want, we can calculate the transistors. I don't have it here, so let's calculate. So here, let me erase. Here we have 6, 2 input NAND, 2 input AND, 6, 6, 6, and 2. So we have 26 transistors for that, and here we have 4, 4, than 2. And we have 14 transistors for that, which is much better. Almost half, 26, 14. So now I would like you to use your intuition and try to simplify this one. So that would be another competition. Let me post question 7, content discussions. Discussions, competition. Okay, so I start a new thread, call it question 7. You should reply to this thread, question 7. So simplification. Okay. So the question is, and some of you might have seen it before because it was there, and if you have downloaded the PowerPoint, you could have seen the question. So the question is this one. W is CD plus A C naught D plus A naught CD plus AB C naught plus A naught BD. Simplify it. I will give you the hint also that the answer would have 3 terms. This one has 1, 2, 3, 4, 5 terms. The answer would have 3 terms with this total of 7 literals. Okay, maybe if you didn't think about it before, so it takes maybe 2 minutes. Let's think about it. Might not be easy and might be easy. It's ad hoc. You might guess something and it worked. You might not guess. Ina, where are you? 3 terms with 7 literals. You see, you have 1, 2, 3. Even if we say it is 3, which is not, then you have lots of literals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Make it simpler. Jonathan, where are you? 7 literals. Jonathan. Cheloi, too much. Shota, too much. More than 7. Oh no, yes. 9. You are 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Done. Done is 6, 6, 8. Close. One more minute, okay? And then we move. Trying? Not trying? Try. Write something on the paper and yeah, it's good. It's playing. You should play. No? No try? Are you trying? Okay, try with a pen. You need pen and paper. It's hard to do it on computer unless you have pen. Digital pen. You need pen and paper. Okay, let's see how is the result. Rida is 7. So if it is correct, then that would be the best answer up to now. Zinat is not good. Zinat is more than, yeah, it is. If we multiply this, then it will become 6 plus 2, 8. Zhaozheng, no, it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No. So up to now, if the answer of Rida is correct, it is correct. Rida, where are you? Okay. Last time I couldn't find you. Rida. Would you like to write it here or no? No, you don't. Okay. Right. So let's see if we have another one or not. I am not sure if Rida is correct, but she wrote 7 literals. Okay, let's go to the answer, okay? One more minute, or no, 30 seconds. 30 seconds. I need one more. Mega is 6 plus 2, 8. If it is correct, then it is not 7. It is like Zinat. It's something like Zinat. Zhao, it is more than 7. Okay, so let's do it. I don't know how Rida did it, but let me show you what I did. Okay, this was the first CD plus A C naught D plus A naught CD naught plus A B C naught plus A naught B D naught. It was 1, 2, 3, 4, 5 terms. Yeah, is that right? It was yes, 5 terms, and 4 of them are have 3 literals, and 1 of them has 2. So what I do is AND this with A plus A naught. and this one with D plus D naught, and this one with C plus C naught. So what do I get? The first one becomes ACD plus A naught CD. The second one, okay, the same, A naught C naught D naught. This one, AB C naught D plus AB C naught D naught. And this one becomes A naught B D naught C, A naught B D naught C plus A naught B C naught D naught. Okay? Up to here, I just added ones, ANDed with ones, and then made distributive. Now, from which one? AD. From this and this, I get AD. From A naught C and A naught C, I get A naught C. And then I have A naught B, C naught, A, B, C in this one, okay, this one. And then let me erase this one. I made it mistake. Up to now, this 5 has gone. And then I have A, B, C naught D, A, B, C naught D, and A naught B, C naught D. From these two, I make B, C naught D, which will be A plus A naught. Okay? And then I have this term, and this term is here, A naught B, C, D naught. Okay? Following? This is what I did. Okay, now what do I have? What do I have? AD. This is AD. This is A naught C, and this is BC D naught. And here again we have BC D naught with something, absorption here, so we have BC D naught. That's it? Oh no, this one. AB C naught D. AB C naught D. Okay, this is again absorption with AD. We have AD here, and we have AD and with BC naught, so absorption. So this is also gone. AD plus AB C naught D, it becomes AD. So only 3 terms with 7 literals. AD plus A naught C. Let's see if Rita had written it correctly. Rita, where are you? Okay, here. AD plus A naught C plus BC. Perfect. So how did you do that? What? Okay, you could do that. Okay, so she was smart to download the slides first. Yes. So how did from here I reach here, yeah? The question is these 2 terms, yeah? Okay. The first one is absorbed with this one. This A, B, C naught D, and AD. You know, AD plus AD and with anything would be AD. So this will go with that. And this one, A naught B, C, D naught, absorbed with this one. B, C, D naught. No, not this one. No, with this one. A naught C with this. A naught C, B, D naught. Okay? Absorbed with that. So this is gone with this, and this is gone with this one. Absorption. Absorption is a very good rule, very good property. I wanted to show you that it needs intuition. there was no systematic method that you could do. So it was some kind of luck. Maybe if you could add this to that, and so on. Now, that is the problem. The problem is this, and we have to find a way to make a systematic method. So using Boolean algebra is some kind of trial and error. I could say it needs some kind of luck, maybe some more practice, more intuition. And we are not sure, at the end also, we are not sure if it is the best. Maybe somebody else could do something better than that. So even the things that I've shown you, 3 terms with 7 literals, you might make it better. It's possible. Actually, it's not possible for that case. I am sure that it is the best, but we don't know. We just reached that point. Maybe we could continue. There is no guideline for the way of minimization in this method. So what we are going to do, we are going to make a graphical notation of truth table which will give us vision of how to minimize the function. So our solution is some kind of visual representation of truth table. And we call this Carnot map. Carnot was the one who presented this method, and the visual representation, it is a map, like a map that we could look at the map and find out how to summarize, how to make it better. So Carnot map. Starting with a simple Carnot map, which for 2 variable Carnot map, and then we go to 3, and then we go to 4. So it gets complicated. First, we start with the simple one, which is 2 variable. For 2 variable Carnot map, we need the truth table is the beginning of each design. For each row of truth table, we corresponded to a cell in the Carnot map. I will show you how. For example, this AND gate. This AND gate, the truth table is this. 0, 0 is 0, and only 1 and 1 is 1. The other one is 0. What we are going to do is to make it a Carnot map. This is the Carnot map of that truth table. This is the Carnot map. You see how it is the same as that one? Look at this very carefully. So for the columns, I am using A. Actually, one column is A naught when A is 0, and one column is A when A is 1. And for the rows, we have B. One row is B0, it means B naught, and the other one is B1, which is B. Oh, this truth table, the first row where A and B both are 0. Which cell correspond to that? A and B both are 0. So this is the cell corresponding to first row. So let me put number on that. So the first row corresponds to this cell, 1. So it's better if you make binary. The first row is 0, 0, 0, and this is 0 also. Okay. The next row is 0, 1. Actually, it is 1. And here, when the B is 1, the B is 1, and A is 0. So this is the 1. Okay? This cell corresponds to that row. The next row, which is row 2, 1, 0. So this is 1, 0. A is 1, B is 0. So this is cell number 2. And the last one is 3, and this is the 3. And if you put the result of the truth table here, we have 0 here, so 0, 0, 0 here, and we have 1 for the cell number 3. So the Carnot map would become something like that. Okay? 4 cells, 0, 0, 0, 1. The same thing that we had it before. But in a 2-dimension graphic representation, a map. And this will give us so many things later, we will see. We will use this map to simplify our design. And these are the rows. So you see the first row is blue, cyan. So the next one is green, and the next one is blue, light blue, and the last one is yellow. So these are corresponding to each. Each row corresponds to a cell. Another example, OR. So OR here, again, you see, OR becomes this. So the row 0 is 0, row 1 is 1, row 2 is 1, and row 3 is 1. So again, the same thing. We could see the Carnot map visually. It is a visualization of the truth table, and it will give us so many things, which we will see later. Yes. So I started with 2 variables. You say 2 variables. Later we go for 3 variables. Okay. Starting from simple and then going to make it more complex. Okay. So this is the corresponding. Now we would like to start our simplification using Carnot map. Well, let's say this is my function, AB plus AB naught plus A naught B. The truth table would become like that. And each in W, product term is any product which has only products inside that. So this is a product term, A, B. This is a product term. This is a product term. For example, if I write A and B plus C, this is not a product term. This has 2 product terms, actually. We should make distributive law, and then it will become 2 product. Okay. Any number of variables added together is called a product term, which I show you. We have another definition. We call it min term if all of the variables is in the product term, all of the variables. So here, again, these are all min terms because we have 2 variables, A and B, both of them are there. But for example, this one, A is a product term because it is a term and it could be a product. But it is not min term. It is another term. So min term is this. And then we have sum of products. Actually, we talked about sum of products before. For sum of products, we said that we go to the truth table, we select all the rows that it has 1 output as the output of 1, and then we make a sum of products of these rows. Each row corresponds to a min term, and when you OR the min terms together, you have a sum of products. So sum of product is any number of variables or terms or together. Here I am not mentioning min term. Later I will make it a standard sum of product which should be min term. Now any variable, anything. For example, for this function that I have written here, since it is too long that I write AB, A naught plus A naught B, sometimes we use these notations, sigma notation. I will say that it is the sum of these numbers. So you know this is 0, this is 1, 2, 3. In our function, we have sum of product of 1, 2, 3. So we write sigma 1, 2, 3. It is easier. They are the same. Sigma 1, 2, 3 is a representation of sum of the products, sum of 3 products, product number 1, number 2, and number 3. But we don't have number 0. Number 0 is 0, so we don't put it in our sum. And these are the min terms. Min term is the term, the product term, which include all the variables. Yes, please.
Just wondering what's the difference between product term and min term? Because you gave the same example.
Yeah, it is. Min term is the product term which contains all the variables. For example, if you have three variables, A, B, C, this is a product term, but it is not a min term. But this is a min term, A, B, C naught, because it has all the three variables inside.
Does it matter whether it's negation or non-negation?
No. You see here there are 8 min terms. 8 min terms, starting from A naught, B naught, C naught, which is min term 0, up to A, B, C, which is min term 7. So we have 8 possible min terms with 3 variables. With 2 variables, we have 4 min terms, M0, M1, M2, M3. And I told you here with this notation, with sigma notation, we use the number of min terms here. So min term 1, min term 2, and min term 3, or together to make this function. And here you see the min terms. Okay. Now another definition, which is a standard sum of products. In a standard sum of products, we have only min terms. If we have only min terms, then it is a standard sum of products. If no min term, for example, here is this SOP, a standard, because it has min terms and it is a sum of products. But for example, if W was A plus B naught, A naught, this is also sum of product, but it is not a standard sum of product. Okay? A plus B naught, A naught. This is it. Yes? Exactly. Yes. If we want to represent the function, the min terms that corresponds to 1 summed together, and it is a standard sum of product because it has min terms. But later you might simplify it and it becomes non-min term. It is a term. It's a product term. But we say a standard sum of product, we want to reach a point which I will give you later. We have a point here. For example, here, this is not a min term. Y is which corresponds to this truth table. Y is A plus B naught C, this one. This is not a standard sum of product, but it is sum of product. In a standard SOP, the products are obtained directly from the Carnot. We will see the Carnot map or truth table because they are the same. Carnot map is the same as truth table, but graphically, visually. W is a standard sum of product. Y is not a standard sum of product. Okay. As I told about a standard sum of product, now I am saying that when you want to start simplification, you start from truth table, and from truth table you bring a standard sum of product, and from there we start our simplification. That's better. So we are sure that from this point, if we start from that point, we will reach to the best possible solution. So starting from the standard SOP, starting from SSOP. For example, this one, we start from this one, and you know this one should be an OR function because it is min terms 1, 2, 3. Min terms 1, 2, 3 are OR because min term 0 is 0 and the rest of min terms are 1. So it is an OR function. But how could we reach to the OR function from here? Again, what we do, we add AB, we add AB here with this AB, and this A naught B, we factor B. With this AB and with this AB and that AB naught, we factor A, then so it becomes this. It becomes A plus B. A plus B. Yeah, we knew it. This is the OR function. min term 1, 2, 3 is OR function. A plus B. Okay, let's come back here. There is a good thing here, if you notice, that if we have two adjacent terms, let's say, for example, this and this. AB is min term 3, and A naught B is min term 2. No, I not. So I made a bad example, and that's the problem of truth table. Let me give you another example. Which one is min term here? For example, this and this. Min term 2 and min term 3. Min term 2 is A, B naught. Min term 3 is A, B. Two adjacent terms could share something and differ with the other elements. Here you see they share A and they are different from B. So if this is the case, you can factor from A and it becomes A times B naught plus B, which will be 1, and this will become A. So if we have terms that they have common parts, but they have only different parts with not of each other. For example, B, B naught, C, C naught, then they are very good candidates to be together, and we will simplify that. Okay? Adjacent terms. We call them adjacent terms. Even by SSOP, considerable insight needed to find the adjacent terms, because, for example, in my example, this term, this min term, and this min term, they are adjacent because they have only they have only one difference in A. This one is A naught B. This one is A B, but they are not adjacent to the adjacent rows, and it is hard to find out that we have to make them together. But in Carnomap, we try to make them adjacent. I show you now. So with truth table, it is hard. In Boolean algebra, we learned that when two terms differed in only one variable, that would be easy. We just factor and they are gone. These terms are called Boolean adjacent terms. But Boolean adjacent terms, they don't reside all adjacent in the truth tables. Some of them are, some of them not. So the structure of Carnomap would be something that make the Boolean adjacent terms adjacent graphically in the map. That's very good. So you could see with your eye, you look at that, you say, oh, okay, they are adjacent. So I have to do something here. Here, for example, this example that we tried to simplify, now we are going to use Carnomap to simplify that. To do that, I have some definitions, some terminology I have to tell you. The first one. So again, these are the corresponding Carnomap. The first one is implicant. Implicant, any term that makes the function 1, any term. For example, AB is an implicant because when AB is 1, we are sure that W is 1. Okay? Another implicant here would be A. You don't see it right now, but A is implicant. Why? Because if A is Y, I am sure that W is if A is 1, I am sure that W is 1 also. Do you agree? When A is 1, then if A is 1, then here. When A is 1, either we have this row or that row, and both of them becomes W becomes 1. So A is also implicant. AB is implicant. A not B is implicant. Okay. So in this example, these are implicants of this function, W. Then we talk about prime implicant. Prime implicant is any implicant that is not covered by any other implicant. For example, the AB implicant somehow is covered by A. A is covering that. When AB is 1, when AB is 1, A is also 1. I will show you in the map. In the map, you see it very perfect, very good. So A and B are prime. Okay, let's look at the map. I will show you in the map. From here, I am going to map. Please pay attention. This is my map. Here I have 3 ones. Looking at this map, I could see that these 2 are adjacent. These 2 are adjacent. Okay, for the time being, just look at this. And from here, I can give you implicant from the map. This is one implicant because it has all 1. So this implicant is B. B, you see, it is B. Again, we have another implicant which is this column, which is all 1, and this implicant is B. Is A. Is A. So we found 2 implicants which has 2 ones. This is another implicant because it is 1, and this implicant is A B naught. This is A B naught. This is another implicant because it is 1. This is another implicant because it is a 1. It makes the function 1, and it is A naught B. A naught B. And this is also implicant AB. But here, now look at the implicants. So I showed you 5 implicants. 1, 2, and the smaller circles, 3, 4, 5 circles. If you look at the implicants, this implicant, the blue one, the blue implicant is covered by this implicant. So it is not a prime implicant. It is already covered by another implicant. The yellow one is covered by this implicant. So it is not a prime implicant. And the green one has been covered by 2 implicants. Both of them are covering that. So this is not a prime implicant. So the prime implicants here are A and B, corresponding to this row and this column. This row, which is A, and this column, which is B. So are you following me? Why do I say this row is B? Anybody has any questions regarding that? All of you understand? You know? At the end of the class. This row is B. Why? Did you see the structure of Karno map? Yes. Yes, B is B. It is B. This row is B naught. This column is A naught. This column is A. So this row is B. Why? Because B is 1 here. B is 1 here. B is 0 in these 2 cells. Okay? This is very important. You have to know, when you look at the Karno map, you see that, okay, here we have B, here we have A. The next definition, so we know implicant, we have known prime implicant. Now the next definition would be essential prime implicant. The essential prime implicant is the implicants that have a cell which is not covered by any other implicant. Again, in our example, let's look at our example. We had 2 prime implicant. Sorry, we had 5 implicants. So the small implicants, these 3 implicants, they have no other cell, so they are not considered right now. And sorry, they are covered already by the prime implicant of this and that. We had 2 prime implicant, A and B. For A and B, are they essential prime implicant? Yes, because B implicant cell which is not covered by any other prime implicant. This cell is only in B. And A is this implicant also essential? Yes, because it has a cell which is not covered by any other prime implicant. So A and B here in our example, both of them are essential prime implicant. So where am I going? I had definitions for you. Now with this definition, I'm going to start simplification. So I guess you have guessed it. You start with essential prime implicant. In this example, my 2 essential prime implicants are these 2. So I start with these 2. I write them. So one of them is A, which is this one, and one of them is B, which is this one. Okay. So up to now, I have written my essential prime implicant. Now I am looking at the Carnot map. Is there any cell that I haven't covered it? This Carnot map has 3 ones, and I already covered it with these 2 prime essential prime implicant. So that's it. So I have made my function. My function would be A plus B, and that's the simplified version of this using Carnot map. Now I go to another example, and then you need to do a lot of practice to find about the Carnot map. So list all EPIs. So EPI was what? Implicant was the terms that make the function 1. From the implicant, you select prime ones. The prime ones are the ones which are not covered by anything else, any other implicant. And then from prime implicants, select the essential ones, which have a cell, another cell which is not covered by any other essential prime implicant. So we list all EPIs, we select them, and then if there is any cell remaining, then we have to pick another implicant. And if not, that's it. We will see another example. So the 2 implicants was this and that, this and this, and it was A plus B. Now we are going to 3-variable Carnot map. I do that, and then we will go to quiz. I guess, yeah, we have time. For 3-variable Carnot map, our map should have 8 cells, of course. So the truth table has 8 rows, so our map has 8 cells. And we arrange them like this. If we are going to arrange them as a binary numbers, 0, 0, 0, 1, 1, 0, 1, 1, this is not good, because, for example, these 2 terms, we would like them to be adjacent, but they are not, because they differ in 2, A and B, which is not good. So what is good? Do you remember a coding that we have discussed first, that each row has only 1 change? What was that? Gray code, yes, gray code. So gray code works here. The gray code is here, works here. We should make our Carnot map based on gray code. And the gray code, we just use it like that. We start from, okay, let me start from the numbers. We start from 0, 1, 2, 3, then skip the turn, 4, 5, then come back, 6, 7. This will become our Carnot map. This is good because you see they have adjacent terms. So what does it mean? Let me show you an example. Here, this is an example. Our truth table has 1, 2, 3, 4 ones. So we need to make a Carnot map, and then this Carnot map has 4 ones. And this is number 4, 1. This corresponds to that. Is 1. So this is also 1. Number 7 is 1. So there are 4 ones in our Carnot map. Okay? Now, going to find the implicants and prime implicants and essential prime implicant. Implicants. The single cell implicants. This is an implicant. This is an implicant. This is an implicant. This is an implicant. For example, one of them, this one. Which term is that? This one corresponds to C, A naught, B. Okay? C, this is AB. A naught, B. So this is A naught, B, C. This implicant is A naught, B, C. This is an implicant. But now we are going to find the prime implicants. Okay, I could say that this is also an implicant. This is also an implicant. This is also an implicant. Okay? So let's see what are they. For example, this one. This, the one that I had rectangles over that. So this one, if you look at that, it has B common in both of them and C. So this one is BC. Let me erase all the inks. This one is BC. Another color. This one, if you look at that, it is A, you see, it is A and C. So A and C naught. C is 0. A and C naught. So this is the one. A, C naught. The other implicant that we have is this one. What is this? This is AB. Yeah, AB. Exactly. AB. So we have 3 implicants. Are they prime? Let's see. Prime is if it is not covered by anything. So, yeah, this is prime because it is not covered completely with any other thing. But, for example, this is an implicant which is A naught, B, C, and this is completely covered by this one, by BC. Yes? So this is not a prime implicant. But the other ones are prime because, for example, even this one, the green one is a prime implicant because it is not covered by completely by any other implicant. You see, the green one has common with yellow, but not completely covered by that. Green one has something common by red, but it is not completely covered. The same thing with red one. Red one has also common with green, but not completely. So both all of the three are prime. Yes. Okay. But now we are going to essential prime implicant. The essential prime implicant is the one that has something which is not covered at all by anything else. Let's see. Green one. The green implicant. The green implicant has this one. Let me put it with blue. The red implicant has this one, which is not covered by any other implicant. So this is an essential prime implicant. So green, the red is essential. Yellow. Yellow again has something that which is not covered by any other implicant. So yellow is also essential. Now let's go to green. Green is not essential because it has two terms. Both of them are covered by other implicants. So AB is not essential prime implicant. Now, what did I tell you? I told you that you start with essential prime implicant, put them there, and see if there is anything left. If we do that, if we put our two essential prime implicants, then it covers everyone, nothing left. So that's it. So our function would be these two and not that. And this is the most simplified of this function. Essential prime implicant. Okay? Okay. So I guess I stop here. We will go to the quiz and then just a little about the projects. So we should be fast. Quiz. Which quiz? We should go. I guess this is the one. Gate realization. So we should start 12:40. So it is 12:47. Six minutes, I guess. I am not sure, but I guess it was 6 minutes. Save and close. Okay, so start it. Let me unhide it. Where is that? Gate realization. How do I do that? Make visible, okay. Start, please. The password is multiplexer. Multiplexer, yes. Gate realization in module, let me show you. Modules. Just refresh your page because I just made it available. Did you get it? Okay, okay. Refresh the page. Multiplexer. So I will give you some ideas about the projects that you could do. The projects are not limited to this. So you get the idea of the project, so you might think of something yourself. And then you tell me, and after my approval, you could do that project. Otherwise, you could select from these projects. The file is in the site. You could download it. What we wanted to do in our course, as I showed you at the beginning of the course, you would in the course you would learn about analysis, design, and implementation of combinational circuits and sequential circuits, and you could design sequential circuits and registers and counters. So this is what we are going to achieve to learn in the projects. The project is the best tool for learning by doing the project. That would be the best, because you would become engineer to design circuit, and you do it in your project. And you remember that it has 20% extra bonus grade marks added to your marks. So it is not mandatory. Anybody who is volunteer or would like to do that, it's welcome to do that. I will give you some ideas. I will give you 10 ideas, but as I told you, it is not limited to that. Since you have the file, I just go through the title. I don't go through the subtask that I've written for you. You go yourself and see which one do you like it, and then announce it. You could do in groups. 2 people or 3 people is good. 1 is not good, make it a group. So 2 or 3, and 4 is not good, 2 or 3. First, design a digital traffic light controller with appropriate timings and sequencing. Yellow, green, red, traffic light. Create a digital vending machine that dispenses different items based on user input. In a vending machine, you go, input something, and then it will give you the one that you wanted. Build a digital security system with password-based access control using combinational logic. So that's a project for combinational logic. Implement a digital elevator controller. Elevator, somebody is asking for the elevator to come, and then it comes there, and then it decides on which floor to stop, and so on. Design a digital alarm system with motion detection. We have motion detection, and based on that, we have also an alarm system. Create a digital game, either like Simon Says or tic-tac-toe, like these games with gates, FPGA and gates. Build a digital audio synthesizer, which will generate audio and different tones. Implement a digital voice changer. The pitch will be changed, so maybe a male voice will become a female, or female will become male, and so the voice is changed. Digital combinational lock. I had some kind of similar project before. And digital stopwatch with lap time measurement and display using sequential logic. So these are just ideas that I've given you. You think yourself and even dream, and then tell me what do you want to build. I will tell you, is it possible for you to do it in this semester, or it is too hard, so don't go to that direction. So either you dream and say, I want to build this, or you select one of these projects. I have other project ideas here also. You might have a look at this. So please select them. In the project section of the course of the virtual or the Brightspace, I start a discussion forum, so everybody who selected a project posts there that I want to do this project. So for each project, we don't accept more than 2 groups. So but for example, this project, you say all of you want to do one. No, just 2 groups at most. My preference is that one group for each project, but if we have reached at end of the projects, then we might accept the next group for that project. So post whatever you would like there with your name, your group mates, and the title of the project you want. I will reply to you. After I reply and I approved, you could start your work. Thank you very much. Have a good weekend. Yes? At the end of the semester. Or even after. I have to see how long do I have to pass your grades. So after the exam, I don't know when do I have to pass the grades. If I have time, so you have time also to do the project.
Just here, like an exam and the quiz.